seconds.
10 seconds.
Good afternoon, everybody. I'm Dick Leatherdale. I'm taking another day off from editing the magazine that we have. Our speaker today is Roger Johnson, and by rights, Roger Johnson should be here doing this introduction because he is the man who organises these lectures. But of course, you can't introduce yourself, can you? Oh, hang on a minute. Roger is perhaps the great authority on the work of Andrew and Kathleen Booth, two people who are not as well known as they should be by comparison with other pioneers. Although I know a little bit about Andrew, I know almost nothing about Kathleen, so I'm looking forward to his lecture today. I think it's safe to say that if it wasn't for Roger, we probably wouldn't have heard of either of those people. And I think that would have been a loss. So Roger, you're the man. It's your turn to come up here and talk. By the way, before we do that, for the people who are remote, if you want to ask questions, can you put the questions on the chat facility on Zoom? Apart from that, I have to say that Roger needs to be away by 4 o'clock. So we will be drawing a line at 4 o'clock sharp.
Right, ladies and gentlemen. Right, we have slides. Excellent, good. As you probably many of you know, I was for many years a member of staff at Birkbeck College, and it was when I first went there as a research student about 1970. We had in the building we were then in a large drum. Now, even in 1970, most of us didn't really know quite what a drum was. It actually was one of A.D. Booth's drums, almost certainly, I think, from MAC, which was the last machine that he built for Birkbeck College. But I have always been interested in their work from those very early days. And so I started researching, first of all, A.D. Booth, who I'll refer to as Andrew. Some of you may well know him as Donald. The family called him Donald. Generally speaking, in public, it was Andrew, and I'll refer to him as Andrew. And also, I will obviously talk about Kathleen, who's really the subject of today's talk. So I was at Birkbeck, hence my interest, and a feeling, as Dick has said, that we give them less credit for a number of their innovations, less credit than perhaps, certainly in my view, than they deserve. So I will share with you today an overview of particularly focusing on Kathleen's life, but inevitably they worked as a couple and as a much more equal couple, and I'll come to that in a moment, but very much as a couple. And I've got many photographs, most of which came from Kathleen and from Andrew Booth. But let me just outline what I would like to do today. It's an interesting story, that their lives, how they came together, and then their working lives together. And there are various other key personalities who form essential, played essential roles in that life. So I'll introduce you to those personalities first, and then go on to talk about Kathleen Booth, as I think we know her, Kathleen Britten, as she was born, and then talk about their pioneering work, and particularly her contribution to it, and her lasting contribution. If there's one thing I would like to hope that I can achieve today, Kathleen Booth, in my view, has for far too long been remembered for coding and testing her husband's computers. I will plead guilty that for quite a number of years, if you listen to my lectures about Andrew Booth, you might well have come away with that impression. That really is to be very unfair, as I'm about to illustrate. Very often acknowledgements come at the end. I think it's helpful, perhaps on this occasion, to put in some acknowledgements at the beginning. I met Andrew Booth. I never met Kathleen Booth. I have exchanged emails in the past and also with Amanda and Ian Booth, their daughter and their son. And the photographs that you will see, many of which I suspect have never actually been shown before, most of the photographs are ones that particularly Andrew Booth sent me over the years and I've kept. I'd like to thank also Martin Campbell Kelly, who had offered to chair today's meeting, but he had a minor surgical procedure on either Monday or Tuesday, which I'm happy to say has gone well. But he drew to my attention a page or so, a couple of pages in his thesis on programming about Kathleen Booth, and I think they're significant. And finally, a thanks to many of you and former friends and former colleagues for encouragement over the years to pursue this. Okay, first person, a man called John Wilson, an industrial chemist. He was the research director of the British Rubber Producers Research Association, who were based at Welwyn Garden City. And he was the research director there from 1937 to 1948. And he has a key role in that he employed, not at the same time, but he employed both Andrew and Kathleen Booth. The Rubber Producers Research Association was an interesting organization in that a visitor noted in 1948, it had 50 employees, 25 of whom had PhDs, and John Wilson gave them complete freedom to pursue problems that interested them. I'm sorry I have to use that picture, which comes off the internet. He's described elsewhere as a bluff, outgoing, middle-aged Yorkshireman. And I saw somewhere on the internet a picture of him sitting in a country pub in a tweed jacket. And I think that is much more the man. He got a military cross and bar in the First World War. So he has a distinguished military record, but I was sorry I couldn't find that other picture. The second person who plays a key role in this story is Desmond Bernal, who was professor of physics at Birkbeck and was a crystallographer. He planned at the end of the Second World War to rebuild his crystallography department with 4 groups. One of the big problems for crystallographers was they were taking X-rays, they had large and complicated sets of equations to solve, and most of it was being done a lot by hand and some of it with simple calculators. He had seen during the war what could be done, particularly in the area of radar. He had no link that I can find at all to Bletchley Park, but he had an interest in electronics. And importantly, he knew John von Neumann and Warren Weaver, who was a director of one part of the Rockefeller Foundation. But Desmond Bernal, then, our second character on the right in that photograph. The next key person, Andrew himself, Andrew Booth. He'd studied mathematics. He was the son of a retired marine engineer. He worked during the Second World War on a PhD at the University of Birmingham on the crystal structure of explosives. And he didn't like doing arithmetic, and he started building hand calculators. And in 1944, he joined the British Rubber Producers Research Association at Welwyn, run by John Wilson, who we have just met. And here is a typical photograph of a Booth, or a part of a Booth calculating device. This one, part of a Fourier calculator. Booth joined Bernal's department in I've had a problem finding the exact date, but it was the end of 1945 at the beginning of 1946. And he was appointed specifically to lead the computational group in Bernal's new department. And he continued building these mechanical and electromechanical calculating devices. Switching sides, to the left there, Warren Weaver was the director of the Division of Natural Sciences at the Rockefeller Foundation. And the Rockefeller Foundation paid substantial amounts of money in the form of research grants, and did so outside the United States. I'll come back to this, but money was extremely tight. It's difficult now to realize how difficult it was immediately after the war to get funding to do anything. Fortunately, Warren Weaver was a friend of J.D. Bernal. And the other component which is important to our story was Warren Weaver is widely credited, I think justifiably, with starting the quest for machine translation of natural languages. And he had this idea back in 1947. He'd been loosely involved with code breaking during the war and thought that natural language translation was actually a similar problem to code breaking. I think that turned out to be wrong, but nonetheless, he was willing to use funds that were under his control to look for ways of addressing the problem. And now we come to the, I think, hero, shall we say, of our story. Kathleen Hilda Valerie Britten, born in 1922. Her father was an inspector of taxes, West Midlands born and bred, attended King Edward VI Grammar School for Girls in Birmingham. 1941, October 41, she went to Royal Holloway College with a college scholarship reading mathematics, and graduated in 1944 with a BSc in special mathematics and won a college prize. So a strong pedigree there in mathematics. It was wartime, and so like many other talented young mathematicians, they were dispatched to the Royal Aircraft Establishment at Farnborough, and she worked there on testing materials used in aircraft construction. And that led in 1950 to a PhD for a thesis entitled Wind Tunnel Blockage. I must own up, I have not read a thesis, I perhaps ought to sometime, but it seems slightly peripheral. Importantly, however, in 1946, with the end of the war, she left RAE, and I think John Wilson at the British Rubber Producers Research Association, looking for bright, really bright young talent, spotted someone to join his team of researchers. Just in order to get this little bit out of the way, some 4 or 5 years later, in 1950, she married Andrew Booth. They had 2 children, Ian and Amanda, who were born shortly before they went to Canada in 1962. And throughout her life, from the 1950s onwards, she suffered from deafness, which severe deafness, as a result of an adverse side effect of medical treatment. So this slide really is there to just give that personal background. Here they are in about 1953. I was sent this picture relatively recently. The family don't know who the rather slightly dismal looking man in the middle is. I thought it might be a relative, but I've no idea. They don't think it is, so we've no idea who the man in the middle is. Right here, so okay, let's get our story underway. It's, I think, fairly well known that in 1946, Andrew Booth paid a 6-week visit to the United States. That it was unusual at that time to be able to get money to go. Bernal organized the trip, and it enabled Andrew Booth to visit many of the sites where work was going on in the United States on digital and analog computers. Probably because it was at the end of the war, Andrew Booth found people not terribly forthcoming in general to a visitor who walked in and said, "Tell me about what you're doing." The one exception to that was John von Neumann, probably because he was a friend of Bernal's, and therefore there was an introduction. And importantly, in July 1946, at the end, just after the visit, A.D. Booth, in his report on the trip, wrote, "I had a long discussion with Dr. von Neumann and came to the conclusion that a machine built in accordance with some of his ideas would revolutionize crystallographic computing." He had been introduced to what is usually called the von Neumann architecture, but basically to that co-authored report about machine architectures. Also, Warren Weaver at the Rockefeller Foundation agreed that Andrew Booth could come back the following year for a 6-month visit. Now, it was extremely unusual to be able to get money. It was an era with currency control and so on. So it was a real privilege that Bernal was able to open that door for them. So he comes back, and Andrew Booth then starts to build a calculator. Throughout many of these slides, I realized where I started doing it. You will find I refer to ADB, Andrew Booth, and KHVB. I started doing this because it's what Andrew Booth did when he sent me photographs. He'd write ADB and KHVB, doing something or other. And I've carried it over onto these slides. So Andrew Booth decided to build this calculator. It was funded by John Wilson from the British rubber producers. And it was a calculator using relays for logic, plugboard sequence control unit. It had no memory, and it used paper tape for input and output. And the comment there, which came from Andrew Booth's note with it, this is a copy of the earliest photograph I have. It was taken in December 1946. And from right to left, we have Kathleen Booth, Xenia Sweeting, who was a research assistant, and Andrew Booth there on the right. So December 46, he starts work on a relay calculator. Later on, it became a relay computer. As I said, it was funded by John Wilson, the rubber producers. There was no space at Birkbeck. Birkbeck had been bombed. The current college buildings had not been completed. They were in the process of being built. So there was no space at Birkbeck. So it was built at the Rubber Producers Research Association. And this photograph, which shows Kathleen on the left there and Xenia Sweeting, and notice soldering irons and so on. The idea that all she did was program is not right. Andrew Booth, and Andrew Booth is not, although in many ways he's had more than, he's had a lot of the limelight, but Andrew Booth recalled that Kathleen and Xenia Sweeting were responsible for most of the construction, both with ARC and then ARC 2, which we'll come to in a moment, which was a redesign of ARC. They did a great deal of the construction of the actual machine. The machine itself had 800 relays. There were 2 racks, a left rack with an adder, subtractor, shift circuits, a right rack which contained multiplier, divider, and the control logic. And it was, according to Andrew Booth, the first relay computer that worked on the binary scale. This is a picture from February 47 of Andrew Booth working on the function table. As I said, with J.D. Bernal's help, he had been able to get Rockefeller to sponsor a 6-month visit to the United States. He chose to go to the Institute of Advanced Studies at Princeton. It's extraordinary generosity given the time. The British rubber producers paid for both to travel first class on the Queen Elizabeth. I think I didn't draw to your attention, but on that first slide with John Wilson, I quoted Andrew Booth as saying that John was a lifelong friend. John Wilson was a lifelong friend. Certainly, he was generous. In those 6 months, they were both able together to travel widely across the United States. They spent a significant amount of time at Princeton, again talking largely to von Neumann. And also there was substantial written output during that visit. The latter part of their trip, they needed to raise some more money, and Andrew Booth earned quite a lot of money on the ladies' dining circuit in the United States. And these ladies who dined were more than happy to contribute to the costs of an attractive young Englishman at that time. During that stay in June 47, Andrew Booth finished his first book. I'll read you just a quick sentence from the introduction. It is a commentary on the rapidity of science progress that since the sections on calculating machinery were written, advances in electronic digital computing have given clear indication that the future of structural crystallography lies in this direction. And that's in the preface, which is dated 1947, and the book is published in 1948. I suspect the preface, or despite the date, may have been written shortly before the book was printed rather than actually in 47. But the book was published by Cambridge in 48. Of more interest to computing was the report published in 2 editions, although the editions are fairly similar, but 2 editions called General Considerations in the Design of All-Purpose Electronic Digital Computer. This is quite a substantial document, 30 some pages. Notice, and I'm sorry, it's slightly small, but you hopefully can see that this report is written by Andrew Booth and by Kathleen Britten, as she then was. And so this shows, in my view, the extent of the contribution that she was making in a document which is not about programming, it's about how you would build a computer and the different options for memory and so on. And I'll say the word more about the contents of this report in a moment. But basically, it discusses the physical considerations for building a computer. Specifically, it makes reference at this point to the use of magnetic drums. And it also makes a special acknowledgement to John von Neumann and to Hermann Goldstein for their help. And they drew heavily on their work, which they saw while they were at Princeton. I'm sorry, this is slightly small, but the contents, the sections in the report covered memory, arithmetic unit, control structures, quite literally how you did it physically. And it also argues, this, sorry, remember this is 1947. This document in the final section argues that there should be a single memory which would handle both the orders as well as the numerical data. So they were well and truly nailing their colours to the von Neumann type mast. But if I just pick out, this section is memories, a brief discussion of thermal memories, optical memories, acoustic memories, serial and parallel, electrical memory, magnetic memory, and so on. So they went, this report goes right through the different options that existed. And then there is a second document, and that was coding for for ARC. Again, written by the two of them together, dated the 1st of September, and again, joint billing for both Andrew and Kathleen Britton. Let me read just briefly here. This, although this report deals specifically with the coding problems for ARC, it can be considered a successor to the previous work. This is because we have made the code of ARC identical with that projected for their electronic machine, which was SEC, which becomes the APEC machines. The advantage of this arrangement is obvious. We shall be able to transfer any problem which has been coded for ARC directly to the electronic machine when this becomes available. In addition, the experience we gain in using the simpler machine may form a valuable guide to possibly advantageous modifications of the code for the faster computer. It's interesting at this very early date, with so limited experience of machines, that unlike so many others who change the orders between machines, that they're talking about using the same order code so that code could simply be moved from one machine to its successor. We'll see that particular issue again later on in a different context. I think, to say a word about what appeared in some of the obituaries in the autumn, which I cannot see a justification for. As an example, the University of Saskatchewan, in a very generous and sympathetic obituary, said, while working on one of their first computers in 1947, Kathleen created a symbolic language to simplify the process of programming the machine. This is now recognized as the world's first assembly language. I just believe this is a misunderstanding. And I discussed this with, one of the things I discussed with Martin Campbell-Kelly. His thesis shows that the instructions and the mnemonics are very closely aligned with the IAS machine at Princeton. And there was, the Booths were always very open with their designs, so on, and shared them. And we'll see a passing reference to that later on. So it's not surprising that rather than reinventing the wheel, they picked up and used ideas that were there at Princeton. And so her assembly language, if you call it, basic is direct, is very closely derived from von Neumann and the IAS work. And so I don't believe this is justified. It's a very small point, but it has suddenly appeared. It appears on various websites. I believe it's just not true. I think it's a misunderstanding which has been picked up and propagated around the internet. One of the interesting products of the visit in 1947 was in March when he arrived. Andrew Booth went to see Warren Weaver, who had funded both his first trip and the second trip. As I said, Warren Weaver had become really keen on natural language translation. Andrew Booth brought with him from Bernal, and Bernal had got support more widely in the University of London for a university computer centre. And Andrew Booth had this document in his briefcase and went to see Warren Weaver, and all of this is in the Rockefeller Foundation archives. And Warren Weaver says basically the fundamentals of numerical calculation are being done, but not non-numeric computing. And at this point, he starts to talk to Andrew Booth about natural language translation, and says basically Rockefeller will provide much of the funding that they're requesting, providing basically you work on natural language processing, natural language translation. Andrew Booth, probably off his own bat, I don't know, but I don't think he can have consulted, basically took the money. And in fairness, they will, as you will see, they worked on natural language for many years after that. But at this, Warren Weaver was really the founding father of it. Again, I apologize for the small print, but it's a remarkable document. We have a copy which was retrieved from a skip outside Birkbeck by a member of the crystallography department many years later, when Bernal, following Bernal's death, and stuff was being literally put in the skip. This is from that research grant application. Just to give you an indication of the problems of the time, it's considered that the static water tank, that's basically a bombed out, it's the basement of a bombed out house. The static water tank at Torrington Square, if roofed in, could make ample provision for the computer centre. The cost of the building operation should not exceed £3,000. I have written research grants, probably many of you have written research grant applications, but I have never asked for money for demolition, a roof, carpentry and joinery, plumbing and drains, and services, well, maybe services of an electrician. But it gives you an idea of really quite how desperate things were that they were having to do this. This is Torrington Square. These houses were demolished, I think, from memory in the 1970s, 1980s. You'll notice this was the building that was occupied by Bernal in Torrington Square, 21 Torrington Square. And in this shot, taken in the 1970s, I think, you'll see the bomb site here. And there, you can see here is the bombed out cellar. This was as it was being demolished to be replaced by Birkbeck's Claw Management Centre in the 1980s. But you can see that space with a roof on it was the computer centre that was built at Birkbeck with Rockefeller money. On the return trip across the Atlantic in 1947, Andrew Booth and Kathleen Britten decided that they would redesign their computer as a quotes von Neumann type stored program computer. And in order to do that, they needed something to act as a single integrated store. And they selected a magnetic store rather than a delay line store that some other groups were using. They also, because of having the integrated store, they needed to extend the order code from the what is now referred to as ARC1 to ARC2. And in December 47, in another grant application to Rockefeller, Andrew Booth wrote, at least it's in his name, regarding ARC, this is of course slow compared with any electronic machine, but will probably be the first working machine embodying a logic code and a memory in which no distinction is made between numbers and orders. And that was a prediction in December 47, and indeed on May the 12th, 1948, and they had an audience. The chairman of the British Rubber Producers Research Association board was present. The machine, of course, was in the BRPRA labs. Quote, we demonstrated the generation and printing of a table of the squares of the natural numbers 0 to 255 in the scale of 10. And that's a quote from Martin Campbell Kelly's thesis, and that's a quote from Kathleen Booth. And so that is the first time that a stored program computer successfully ran a program. It's not an electronic computer, it's an electromechanical relay computer, but it is about 6 weeks before the Manchester Baby, which was the world's first electronic stored program computer. So that is a date which deserves much more prominence in the history of computing at that time than it has. And I'm grateful. The date has been in the paperwork. It's in Metropolis, for instance, if you read that book, and there's references to it elsewhere. Martin Campbell Kelly drew that to my attention several weeks ago now, when I was putting these slides together, and I'm grateful for him for prompting to draw attention to it. And here is Kathleen Booth standing in front of the arithmetic unit, which was one of the 2 major racks, and Kathleen Booth here with the arithmetic unit of ARC2, which she constructed. This, I emphasize this because we really need to understand that she had far more skills than just as a programmer, even though since she did do the programming, I think there is little doubt that Kathleen Booth actually wrote the first program to run on a stored program computer. And that is something that she deserves credit for. So as we've seen pictures of her with the soldering iron and so on, and here in front of the unit that she built. She is both a software engineer, to use modern terminology, but also an electrical engineer, electronic engineer. It's worth just saying briefly that they brought back this strange voice recording machine. These were intended for managers, and they had a paper disc, if I could call it that, which had a magnetized paper on here. And it was intended for managers traveling in the United States to record, to dictate letters for someone in an office to type for them. And indeed, the paper could be folded up and put in an envelope and posted back to an office. They brought one of these back with them, tried to make it work and couldn't, and then moved on to the drum. Many of you will be familiar with this picture, which is the prototype drum that they made. Just really just a small test bed, and that was the world's first rotating storage device with a magnetic storage. That's in the Science Museum. It was on display for a number of years. It's now in the store. And they then went on, having made that little miniature proof of concept, they went on to build a larger drum, and this was built to run on 256 21-bit binary numbers, 50 digits per inch on the drum, revolving at 3000 RPM. And the ARC2 was, quotes, debugged completely on, as we said, that date in 1948. The drum was subsequently reused on the electronic successor to ARC2. That drum is also in the care of the Science Museum. When I last saw it, it had various screws missing and it was in a rather fragile state, but it was there. They, as I say, went on and reused that drum, and they built this drum to go on ARC2. And this is a remarkable object. Basically, when they took the drum away, they then needed something on which they could store instructions. They needed for ARC2 to have a means of having a program and a data store. This was used as the data store. The store had 32 21-bit words, and it used a plug board for the instructions, 300 instructions on a plug board. And ARC2 was running in doing simple calculations and so on, routine calculations in the crystallography department, and at least until 1954. The drum is it's catalogued in the Birmingham Museum. Chris Burton wrote a study of it and how to conserve it for us in about 2002, 2003. So we have an inventory number for it, but the Birmingham Museum, after it moved into its present modern home, you cannot find it. If you go into this massive warehouse full of plastic containers, you can kind of understand how things are lost. It's an extraordinary device, which I would dearly love to put on display, possibly at TNMOC. The way it works is the bits are literally represented by small plastic beads that are, as it were, naught one way, one the other. And there are fingers here which move the beads, and another set of fingers that sense when there is a bead present. It's a most extraordinary device. It would be lovely to have on display. Okay, so I said that they agreed to work on natural language processing, and less than a year later, Warren Weaver and Gerard Pomerat actually are in the UK, so they go and visit the British rubber producers to see what they're getting for their money, which they had contributed. And again, I quote from Warren Weaver's notes in the Rockefeller Archive. Weaver writes, Miss Britten, is in charge of their computing laboratory. When we arrive, ARC2 suddenly refuses to function, but they soon trace the responsible relay, which is burned closed. And then there's a few other sentences. And then Warren Weaver, ever the optimist, writes, so far, they have not considered the problem of multiple meanings, i.e. words that have more than one meaning in the English language. Given the tiny size of the machine, it seems to me extraordinary and suggests almost a sort of naivety on remarkable given his intellectual capabilities on Warren Weaver's part. But this is what he wrote. Ambiguity has not been solved. Well, that remains something of a problem even today. As I said, Kathleen Booth and Andrew Booth, and latterly mainly Kathleen Booth, worked on natural language processing. It was a major activity in the department at Birkbeck. We'll come back. This is November 1955, which was the first public demonstration of translation. But there are books here. It's Greek to the computer, which they were Andrew Morton. This is a book to do with biblical Greek and the authorship of Paul's letters, if I remember rightly. Mechanical resolution of linguistic problems is a serious academic piece of work. And then again from the same group, the settlement of Polynesia, a computer simulation. All of these works, those coming from Birkbeck, and they continued this work in Canada, where of course, being a bilingual country with English and French as languages, it was a hot topic there. The work was still going, there was still linguistics work when I arrived in Birkbeck in the 1970s. So Warren Weaver certainly got his money's worth out of their activity. Let me just talk briefly about their ideas. And I do believe that from reading that even though quite a lot of the writing is in Andrew Booth's own name, it's clear that they talked about these things together and discussed them. So just because it's got one name on, I think you can see the influence. You can see it as the influence and work of both of them. If you think back to the days in the 1940s, early 1950s, the head of MPL said the UK might need 3 computers. At that same time, Andrew Booth was planning to build a computer that was cheap enough so every university could have one. All through their work, they consistently argued that let's make computing accessible as widely as possible. They were always promoting new applications rather than just concentrating on numerical calculation, for instance. They were looking at new areas. I remember the last time I met when Andrew Booth came over in 2005 for it was awarded a college fellowship at Birkbeck. He was grilling me on what applications the department was pursuing, and and saying you ought to be looking at this and this, it was I think the way their minds worked, and so they worked natural language, text processing, voice input techniques, game playing. Most of their books contain chapters towards the end on applications, ideas, encouraging people to think about using the computer more creatively. And indeed, there are 2 books actually about applications. The Automation and Computing in 1958, and then Digital Computers in Action, which is a more popular book in style, in 1965. It's also worth commenting, they shared their designs very freely. I just skipped over it in the interests of time. But the design of ARC was made freely available to Van Wijngaarden in Holland. And as we'll see in a moment, the successor to SEC was made available widely. SEC, it was the promised electronic version of ARC2. It was a two-address machine using the drum. Slightly different stories. Booth in an interview said it was completed in 1949. Norman Kitts, who is the research student there, said it was not fully working in 1951. I suspect that all the components worked, but not necessarily all at the same time. And Norman Kitts was Birkbeck's first, as far as we can see, first computing graduate. Norman Kitts is an interesting man, and I'll come back to him in a moment. So a document turned up, which is probably largely unknown. It was drawn to my attention by Hamish Carmichael, who a number of the older or more long-serving members at CCS will fondly remember. Hamish was helping catalogue Science Museum papers. He came across this report, a design for a desk electronic computer. This is July 1950. And the sponsors, it's not quite clear, but it appears to be the Department for Scientific and Industrial Research, Government Department, and or the National Research and Development Corporation, NRDC. The report is in two sections, logical and physical, and it's rather like the 1947 paper on how to build a computer. It saw one of the major issues for a desktop machine of actually displaying the output. That was a major problem. The report was written by Norman Kitts, it was written while Norman Kitts was in the department. And Norman Kitts, who was building SEC at that stage, went on to build Anita some years later. And I do wonder whether the idea of a desktop calculator, at least, might have been put into Norman Kitts's mind during that time. We're familiar with the Booth multiplier, which is used in millions, billions of chips produced each year, and that the two of them sat together in a tea shop in Southampton Row in central London and worked out the details of the Booth multiplier. They then went on to produce probably their most famous machines, the APEC computer. The first one John Wilson had moved from the rubber producers to the rayon. Sorry, I've got that title wrong. It's the Rayon Research, not Rayon Producers, Rayon Research Association. And they produced a second, slightly larger version of it, the crystallographers. Interestingly, their design, which, as I say, they made freely available, led to a machine, essentially a copy, being built in Norway. And of course, the story of the HEC is well known. And interestingly, the Italians have recently been in contact because a copy of APEC was built in Italy. Here is the first one. This is the one that Bird copied to give the prototype for HEC. Here's the output. These are slides I've shown before. Here is HEC 1, and that has been on display for some years at TNMOC, and it went on. It was the first mass-produced best-selling computer in the UK. Here is a picture which you won't have seen before, which is of the Italian version, which was produced at the University of Padua. And it was built around 1960. Here is the X-ray machine, the one for the Birkbeck department. Interestingly, it was sold to what was then Battersea Polytechnic, which became one of the key parts of the University of Surrey. It was sold to them in 1957, and I have a letter which suggests it was scrapped about 10 years later, but they never really got it to work properly, is what the letter said. Here is a picture of Kathleen Booth with paper tape in hand. The apex has a main memory with a drum, 256 tracks with 32 words and 32 bits. Kathleen Booth, in her book on programming, talks at some length about optimum programming, which is it's a two-address machine. So instructions don't have to be sequential. You can basically put them where you like and just go to that the numbered instruction. And by placing the instructions at suitable intervals around the drum, you can significantly improve the performance. I think fortunately, with the passing of the drum, that problem moved away. Apex was followed by the Mac. Only one of these was built. This is a picture of it in the static water tank at Birkbeck. Now, if we are lucky, going to sorry, there is a sorry, there's a piece of video, but it doesn't seem to want to play. The synchronization has gone, sorry, between the soundtrack and the synchronization slightly gone. If by chance anybody watching knows which of the news companies that was done by, I would be very grateful to know, because it would be very useful to get a copy of that full piece, because you saw at the end a picture of a chessboard, and I think therefore there is more to that piece that would have been shown if the Mac was followed by the M2. 3 of these were built funded by the University of London. One went to King's College. One went to University College, who immediately called it UCC, University College Computer. Nothing to do with those gentlemen down the road. And a third was ordered by Imperial, but I can find no trace that that was ever completed and delivered. Here is the drum. This is the drum that as a young student I first saw. It's just worth in passing saying a few words. The Booths created the Department of Numerical Automation, which became the Department of Computer Science. It appears that they were successful in creating the world's first academic department devoted to computing. Most other universities had either computer centers or computer laboratories. They were not yet given academic status of an academic department. There was this nice picture taken in the garden at Penny Compton, where the Booths lived, and the department was growing. People sometimes suggest it was always a very small department. Here are a variety of people enjoying a get-together in the summer of 1960. There then came this breach between Birkbeck and the Booths. Andrew Booth basically had raised the funds for a chair in computer engineering at Birkbeck. It was turned down because of academic politics, frankly. Andrew Booth described it as petty academic jealousies. Looking back, it's just almost incomprehensible. But it meant that they left really quite suddenly and went to the University of Saskatchewan. Kathleen Booth was appointed as a lecturer and research fellow. She ran a project for a number of years on machine translation between English and French. She also spent quite a lot of time in Canada as a champion for women in engineering and science. Andrew became the Dean of Engineering there. And then in 1972, he was appointed president at Lakehead University. And for contractual reasons, Kathleen Booth couldn't be appointed as a paid member of staff. And so she was given an honorary research fellowship and continued working on machine translation. An area where it's very tantalizing is the area of neural nets. Kathleen Booth was clearly very early in the field of neural nets. In 1958 and 59, Birkbeck's annual report says she was developing a program to simulate neural net to investigate ways in which animals recognize patterns. The following year, she's working on a neural net for character recognition. And nothing was published. There is nothing that I can find in the literature. And I've inquired of the family if they have notebooks or anything that might give more details, but those details seem to be lost. In 1993, she published another neural net paper with her son Ian on neural nets to identify marine mammals. Ian has published numerous papers with his father and on his own and with others, mostly mathematical or statistical, but particularly those with his father. The Times obituary says, after retiring, they, not just one, not Andrew, they started a computing consulting business, Autonetics Research. It led to a long association with the Canadian Department of National Defence and the Institute of Ocean Sciences in British Columbia, looking at acoustic modelling, the effects of ocean shipping noise on the communication of marine animals. We can see going back Kathleen's interest in animals and in marine animals as well. I think we can probably guess what acoustic modelling in the context of national defence is primarily about. And not surprisingly, you find, apart from that one paper, you find nothing about that, certainly, in the literature. Kathleen and Andrew had family holidays on Vancouver Island, and they bought a house there. And when they retired, that was where they went. This is a post-retirement picture, and they enjoyed the countryside, hiking. And Kathleen also grew prize-winning vegetables in her retirement. And here's a picture which they sent us a year before Andrew Booth died. But let me conclude. Kathleen Booth was sadly one of the last of the UK pioneers. There are very few left. Mike Woodger, I see, is about to celebrate his 100th birthday. Has just celebrated, which is wonderful. But there are very few now who go back to the 1940s. What I hope I've been able to do in this lecture is really to show you Kathleen Booth as an electrical engineer, software engineer, natural language pioneer over many years, a first-rate mathematician, a keen advocate for women in science and engineering, and so much more. I really do believe it was a long life and a life well lived.
Thank you, Roger. We have about 20 minutes for questions and comments on the chat, but if anybody in the room has got anything to say, be happy to take that. I've got something to say. I was, as an ex-Manchester person, shocked to hear that somebody had run a stored program computer before Kilburn. But I do tend to agree with you, Roger, that the fact of running a stored program computer is rather more important than the technology employed. I'm happy to acknowledge that myself. But right, anybody else? Yes.
The connection with the Rubber Association. My grandfather was involved with something to do with rubber. After he was in the civil service, he then ended up as chairman of Pirelli in the UK. But he had some connection with rubber. And I'm just wondering if it's going to have any connection with this British Rubber Association you mentioned.
Well, the British Rubber Producers Research Association was an activity that all of the government promoted industry sector research associations. John Wilson went on to the Rayon Research Association. They promoted and they were funded, the rubber producers were funded, I've forgotten, something like a halfpenny a bale for every bale of rubber that came into the UK. I think the unit is a halfpenny, but don't quote me on how much rubber. So there was a simple industry-wide payment, and then the results were shared amongst the industries, and it was a way really for the government to promote the building up of the industry. The rubber producers did in wartime quite a lot of work, and so these were what we call sort of national infrastructure type organizations. I mean, they were important. They've been important in before the war, but particularly during the war.
Okay. Anyone? Yes.
If you were starting numerical applications with simple computers, you wouldn't have thought that crystallographic calculations were the point to start, because you've got so many Fourier series to sum they're long series and they contain trig functions. I would have thought there'd been much simpler applications in, say, mechanical engineering, sort of, stress and strain problems and things that could be solved more simply. Because the simplest crystallographic problems involves a lot of computing.
Yeah, I should perhaps say for the benefit of the audience that David Moss, who's just Professor David Moss, is a professor of crystallography at Birkbeck, and is he and I were colleagues at Birkbeck together. I think you're right, David. It in a sense goes back to my opening pictures of Bernal and Warren Weaver and John Wilson. If the Booths had not, in a sense, been in their sphere of influence, then they would not have developed in the way that they did. It was because Booth had done crystallography, although Bernal did not recruit him for his crystallographic experience, but for his ideas on computing, calculating. And it was a long time, I suspect, before they really were able to do a great deal in terms of serious crystallographic calculation. But there was an ambition, but it was, I think, a coming together of all these disparate people who by chance had a shared interest. Warren Weaver was heavily interested in crystallography, Bernal, and so on. So I think, although it's a bit like their early work on natural language processing. When you look, that little clip I showed was 1955. By then, it was 8 years since Warren Weaver had said to A.D. Booth, here is some money, go and translate natural language for me. And all they're managing is not much more than a simple word lookup and substitution. So
I think the point is that crystallography was pretty well frozen and unable to progress because of the lack of processing, and therefore they were very keen to push for computer support, even though it was a difficult problem.
I heard that the early crystallographic calculations, you had to run them a number of times until you got the same result twice. Could it accept it?
Sorry, you needed to run it because the computer would give you different answers to the same.
Yes, until you got the same result twice.
Right. I don't know why a program should run differently on different occasions.
Well, maybe the different components failing.
No, I think it was more that you were homing in on the right solution by iteration. It wasn't that the results were different, but rather like doing a square root by repeated division.
Yes.
So when did the FFT get in? The fast Fourier transform, a hardware way of doing some of the calculations.
I don't know.
I stopped being a crystallographer in 1970, and it doesn't seem to have arrived as a piece of hardware by then.
In software, it was, I think, about somewhere around in the 1980s, I think, we started using FFT.
I have a contribution on chat from somebody called Anthony, who is now scrolled off the top of my screen. If you'd like to unmute yourself, Anthony, and make your comments, that'd be grateful. Look very interesting.
Well, can you hear me?
Yes.
Well, I was just saying that in the mid 1960s, I was actually working at City University, but about once a week we used to go to Imperial College because there were afternoon seminars on all sorts of topics. And I do remember that was a time when I did go to a talk by A.D. Booth, and it was about translating natural languages. And, you know, I was a young guy at the time comparatively, and I thought it was an idea that would never work. And I knew enough about languages to see it was completely a very difficult problem. But then much later, I was in British Columbia, and I was somehow in connection with that, I was aware that there was some interest in this sort of thing at University of Saskatchewan, I think perhaps Kathleen Booth was there, but certainly there were activities in Saskatchewan of that sort of activity. That was really all my comments. Thank you.
Yeah, certainly the Booths took natural language processing with them to Saskatchewan. So they might have by then have moved on, but either they were there or that was work that they had seeded in the department there.
Yes, and of course, in Canada, as somebody mentioned, the fact that everything has got to be in English and Canadian, or however you describe these two languages, means there's a great need to have two equivalent ways of saying the same thing, one in each language, and they've got to be somehow pretty accurate. Otherwise, you get all sorts of stupid misunderstandings.
Are we done?
Dan's got-
Dan.
A couple of interesting points about mathematics. In the dramatization of the story of the discovery of DNA, there's a point at which Crick and Watson, the dramatic characters, are absolutely furious at the fact that Franklin is contemplating calculating the form of the crystal by having a room full of people work for about 9 months, is what they reckoned it would take. Whereas Crick and Watson go off and take an inspired guess, the first one of which is wrong, and then they correct their view and come up with a double helix. But in another example, my wife's uncle became director of the Rubber Research Association at one point. And his background was actually in mathematical ballistics, he was a graduate at the beginning of the war. And he ended up, the family story was that he was given a lorry and told to go and steal the German synthetic rubber industry. In fact, his job was to go and value it in terms of reparations. But again, there was a link between his background in mathematics and his eventual successful career in being, as the family says, something big in rubber.
Right. Well, thank you for that, Dan. It remains for me to thank people. Thank people, the 70 or so people who've come in on Zoom today. To thank the people who are here in rather more numbers than we've had recently. Thank you for making the effort. Most of all, I have to thank Roger. Roger for destroying my long-held suspicion that Manchester was the first in some way to run a proper computer. Now it's turned out here in London. Roger, I think your last slide, or almost last slide, long life is very appropriate. And you have given us today some light on a story which has been dark for far too long. Thank you so much.